saw this thing about you are given a congruence AX congruent to B mod n, and you want to find NX such that this is true. Right? Does it exist? Does it not exist? And what's the condition under which it exists? If it exists, then can you use the multiplicative inverse to find it? And maybe the multiplicative inverse does not exist, but can you still solve the congruence? Are there any questions? Please. Okay, so otherwise let's move to solving a system of congruences. Okay? So this lecture, what we want to do is we are given two congruences, and we want to find an X that simultaneously satisfies both these congruences. So it is just like a system of linear equations. So first you start trying to solve one linear equation. Right? You draw a straight line, try to find points. And then you are given multiple lines and you want to find points that intersect these lines. Just like that, there are applications where we want to solve a system of congruences. And similar to single congruence, we want to ask, does there always exist a solution? Under what conditions can we say that a solution exists? If it exists, how do we find them? And so on. Okay, so whatever we will see today, we'll have applications to the next lecture where we will actually show this protocol, RSA, which is used in cryptography. So it's a protocol messages. So we'll see how to solve the system of congruences today, and we'll see some applications next. So did anybody try to see how to solve this? There are two equations here, 1 and 2. This was given at the end of the previous lecture. Okay, so what do we have? We have that X is congruent to 4 mod 8. Okay, that's the second equation. So this tells us that 8 must divide X minus 4, okay, by the definition of congruence. So this means that you can write X minus 4 as 8 times K for some natural number K. So X is equal to 8K plus 4. So this is one equation that we get. Now what we need to do is we want to find if these X's also satisfy the first congruence. So what should we do for that? Just as you do in the case of linear equations. So you know that these are solutions to the second congruence, right? So these kinds of X's that when divided by 8 leave remainder 4 are answers to this congruence. Now I want to ask whether these X's also satisfy this congruence. So what should I do?
Substitute it in the.
You have to substitute it, right? So you also want to solve X is congruent to 2 mod 5. Now the question is, does 8K plus 4, is this congruent to 2 mod 5? Right? So you can subtract 4 on both sides because we know that we can subtract on both sides of the congruence. So you will get minus 2 mod 5. Okay. So we can subtract 5K so that I can divide. So we get that 3K is congruent to 3 mod 5. Now I know that K is congruent to 1 mod 5. Can cancel 3 because I have that they are co-prime. Right? In other words, the multiplicative inverse of 3 modulo 5 is 1. That's another way to see it. So I know that K is congruent to 1 mod 5. This is what I get by substitution. So this means that my K should be equal to some phi L plus 1. Right? So let's substitute this in 3. You get that X is equal to 8 times. Okay, so this is 5. Right? So 40n plus 12. Right? So the solutions are 8 is equal to 40L plus 12 for some L in N, or some L integers. Actually. Yeah, even this should have been integers. We have been talking about integers. Okay, so when somebody asks you what is the solution to the system of congruences, it is all those numbers that when divided by 40 leave remainder 12. Right, so this here is a solution to this system of congruences. Is this clear? So this method is called back substitution because you begin with the second equation and then you substitute back. We had seen this earlier also. So let's do one more example to demonstrate something slightly stronger. Let's say we have this. So then this is 1, and 3x is congruent to 4 mod 8. This is the second equation. So maybe you can take a minute and try to figure out how to solve this. So you have to try and solve the congruences one by one, right, just as we did earlier, and try to do some substitution. Let's see. So maybe you can try and tell me for what values of x this is true. So I will leave this as an exercise. Try to do this. So this has a solution. Okay, so there is a solution, and you can try to figure out what that is. So you have to bring an expression of this kind. Okay. So here is another example. Okay, so let's look at this example. X is congruent to 3 mod 4, and x is congruent to 0 mod 6. So can you try this? Maybe you can take like few minutes.
No, ma'am.
Did anybody?
It
Okay,
does not have.
what's new? Okay, so let's try to do this. So what does the first equation tell us? That when you divide the number by 4, it leaves remainder 3, right? So x is equal to 4k plus 3 for some k, which is an integer. Okay. So now, as usual, let's just back substitute, right? So you will get that 4k plus 3 is congruent to 0 mod 6. So the first thing you should think about it is the left-hand side has 4k plus 3, so I have to get rid of this constant. Right? Only then I can find the multiplicative inverse or something like that, right? So that I can see for what values of k this is true and then substitute it in this equation for x. So I have to subtract 3, so I'll get 4k is minus 3 mod 6. Okay. So now what does this mean? This means that 6 divides 4k plus 3. Or in other words, 4k plus 3 is equal to 6 times L. So 4k minus 6L is equal to minus 3. So this is a linear equation. It has integer coefficients, and we are looking at integer solutions for this equation. So does this equation have a solution? in some of the previous lectures we had seen, right? How to find whether a linear Diophantine equation has a solution or not. So can there exist K and L such that 4K minus 6L is equal to minus 3?
No.
Which is not possible, right? So why is this? So by this theorem that we had seen, right? For ax plus by equal to c, for a solution to exist, integer solution to exist, we know that the GCD of AB should divide C, right? So what is the GCD of 4, 6, which is 2, right? This number does not divide 3. Right? So this implies that the above system of congruences does not have a solution. Plus by equal to c as a solution. GCD. So is this clear? Why? So not all system of congruences have solutions. So that is the big takeaway, right?
Yes, ma'am. Or we could have seen that x is an odd number because x is 3 mod 4, and so like 6 can't divide x.
Correct. Yeah. But always this odd even might not happen, right? So generally it might be that you would reach a situation in which you have a linear Diophantine equation where this GCD is not. In fact, why should it be just 2 congruences? Right? We can have like 5 congruences, 6 congruences, or I may give you a list of like 20 congruences and ask you to find the solution. So then this back substitution is sort of inefficient because we had only 2, right? We were able to substitute. If I gave you 15 congruences, you will keep doing this, and in the last congruence, you might figure out that there does not exist a solution. Okay? So we want to understand when a solution exists and when it does not. But what she said is right. For this example, it is true. This odd even itself argument itself would have been. It's scaled correctly, right? So now systems of congruences are solvable. So now we want to see what is true about this. So for this, there exists a solution. I want you to find out the solution as an exercise, but it does have a solution. So what is true about this, but not true about this, or what is true about this congruence? So what is true about these numbers, right? Or these ones here. So if I have AX is congruent to B mod C and some BX is congruent to E mod, let's say some other number, E mod P, what is it that should be true about these numbers that can let us solve these congruences? Right? So that's what we want to see next. So for general example, let's consider I have X is congruent to A1 mod N N1 and X is congruent to A2 mod N2. So can someone see what should be true? Like what wasn't true here that is true in the other examples?
N1 and N2 are co-prime.
So let's try to see why this condition should be true. This back substitution only. Let us try to do the back substitution and see what happens. Right? So from the first equation, we know that x has to be x when divided by n1 leaves remainder a1, right? So x is some k1 n1 plus a1, where k1 is an integer. Right? And just like we did substitution, now I have one possible solution to x. I'm going to substitute the second equation. So I have k1 n1 plus a1 is congruent to a2 mod n2. Right? So what do we know? We know that so this when divided by n2 leaves remainder a2. Right? So k1 n1 plus a1 is equal to k2 n2 plus a2. K2 is some integer. So we have k1 n1 minus k2 n2 is equal to a2 minus a1. Okay. So what are the unknowns here? K1, K2, right? So A1, A2 is given to us as part of the congruence itself. I know A1, A2, I know N1, N2. So these things are known to me. So I have to solve for K1, K2. So when does this have a solution? When does this equation have a solution according to Bezout's theorem?
GCD N1 N2 divides A2 minus.
GCD of N1, N2 divides A2 minus A1, right? But now I don't know what A2 minus A1 is. So what is that number that I can fix the GCD of N1, N2 to be to guarantee that no matter what A1, A2 is, there will be a solution?
1.
1, right? So if this is true, then certainly there exists a solution. Is this clear to everybody? Actually, what I would have wanted is I just want GCD of N1, N2 to divide A2 minus A1. But the problem I have, I do not have any control on A2 and A1 because that is given to me as part of the problem. So the only thing I can guarantee is as long as GCD of N1 and N2 is 1, definitely there is a solution. Congruences. Okay. So this means that whenever N1 and N2 are relatively prime, I can find a solution to the system of congruences. Okay. So now can actually find a solution. So what should it be? As soon as I give you these two congruences, can you split out the solution, right, by using division? Now have right. So in terms of K1 and K2, I want to will go away, go modulo into then this term will go away. We can see that the reminders are as you require them. So the moment you are given these two congruences, if you know that N1 and N2 are relatively prime, then you can split out this. Okay, is this clear? So now we want to generalize this, right? So here we had only two congruences, so we were able to do this. Now the question is this true for a system of congruences? So what are the kinds of congruences we are looking at? A1 mod N1. So this is the system of congruences. So I want N1, N2, Nk to be relatively prime. And A1 to AK can be any arbitrary integers. We don't really care. So now we want to ask whether there exists a solution to this. In fact, it does, right? Just like we saw for two congruences, it is true about any number of congruences. So there is a solution.
Shouldn't they be pairwise relatively prime?
Yes. Yeah. So when I mean relatively prime, yes. Pairwise. So what we mean by that is for any ij, ni co-prime to ij. So then there is a solution. That's right. Yeah, true. Thanks. So because relatively prime is about two numbers. Right? So there is a solution which is an integer, right, such that the above congruence is good. Now, the other question that you want to ask is, can there be many solutions? Can I come up with an x which is which is like 40L plus 12, and somebody else comes up with another solution, which is 20K plus 3? Is that possible? So these solutions are unique up to modulo. What do I mean by that? So this solution x is unique modulo the product of these numbers. So modulo n, where this capital N is N1 into N2. We will see why this is true, how to show that it is true, and so on. But at least what is going on should be clear fairly. So this theorem is called the Chinese remainder theorem. It's called CRP for short. And it has several applications. Right? So this was done by a Chinese mathematician. It was proved later on. It was stated by a Chinese mathematician about, it's just a statement about integers. Right? So it was stated in this form, like very early on result. So it was stated like this. So there is a number which when divided by n1 leaves remainder a1, and a number divided by n2 leaves remainder a2, and so on. Is there a solution to this? Right? It can be stated in terms of apples and oranges also, like some sort of a trading. Okay, so we want to prove this, but is the statement clear? So now one question that could occur is, what if these ni's are not relatively prime, right? In that case, is there some other condition under which the solution is true? I mean, a solution exists. So that we will see. But when these ni's are relatively prime, first we want to say that there is a solution, and the solution is somewhat unique. It's unique up to the product of these relatively prime numbers, in the sense that if I divide by this term capital N, you will all get the same remainders, right? No matter what excess you come up with. Okay. So let us see a proof of this. Oh, so by the way, I wanted to mention, so all of this, these things actually exist for polynomials also. Like for those of you who are interested in higher mathematics, you can look at it. For example, why should these a1, n1, all of these be integers, right? They can be polynomials. But then for these things to be true, we have to define what polynomial division is, right? Where you divide one polynomial by another polynomial. Even that is immediately not clear. Right? For example, if I ask you to divide 3x squared plus 2 x1 square plus 2x2 square by some other polynomial, like how do you define the quotient? How do you define the remainder? What's an algorithm, right, to do this? So these things, or you're given two polynomials and you want to find the GCD of these two polynomials. So these things also work for polynomials, and Chinese remainder theorem is also true about polynomials. But yeah, these probably will be done in some graduate course. We are here interested only about integers. So let's try to prove this. So now we have that n is this number n1, n2, so on. So for convenience, I just want to define this another number ni, which is capital N by ni. Okay. So this is just n1 to nk divided by ni. So it's the product that will just miss I. It's all those nj such that j is not equal to I. So what can you say about the GCD of ni and ni? I know that these ni's are relatively prime. And in fact, if you look at it, I'm actually doing exactly what we did for the two congruences case. Right? So there also we did something similar. So maybe when the proof is complete, you'll be able to see that we are doing nothing here in this proof that we did not do there. It's similar to the back substitution, if you unwind it. But maybe you can go home and do this as an exercise. Like, why is this proof similar to this one here? So now I know the GCD of n1 and n2 are 1. So what can I say about the GCD of n1 and m1?
It's 1.
It's 1. So You can actually prove that because this product contains every other number that is relatively prime to n. There cannot be common prime factors between this and this. If there was a factor p that divided ni and this product, it should divide one of the nj's, right? Then this means that ni and nj are not relatively prime. Okay? So what does this immediately tell us? The moment the GCD of ni and mi is 1, and we are trying to go modulo ns. Right? What can you say about the multiplicative inverse? The moment I know that the GCD is 1. So I can say that the multiplicative inverse of mi modulo ni exists, right? Because the GCD is 1. Nothing fancy, whatever we saw. Let's call this inverse, right, yi. So yi is the multiplicative inverse of mi, right, modulo n. Okay, so now what we have is, we started with numbers n1 to nk, and we define numbers m1 to mk. Because the GCD of each mi and ni is 1, I know that there exists y1 to yk. Right? Which are multiplicative inverses of these mi's modulo ns. Okay. So now I want to construct a solution. So can someone try to define a solution? So you have to use these y's. So remember that we also have a1 to ak. So just like we did it here. So can you use the mi's, the yi's, and the ai's to come up with a solution x that satisfies all these congruences? So what do we actually want to do, right? I have x. I want this to be congruent to ai mod ni, right? Let me just write it in a different color and then erase it. So I want x to be congruent to ai mod ni. Right? So if I multiply by yi and mi, is this true? Like, is this true? As in, if this is satisfied, can we say that this is satisfied? We can, right? Because mi is the multiplicative inverse of yi modulo ni. So yi mi is congruent to 1 mod ni. So this is essentially the same as saying that x is congruent to ai mod ni. So now what should be the solution? Now I have these yi's, and I know that if xi is congruent to yi ai mi mod ni, then I'm fine. But I want this to be true for all the ni's. Right? So what should I do? So what do we want to do? We want to come up with an x which, when divided by n1, leaves remainder a1, divided by n2 leaves remainder a2, divided by nk leaves remainder exactly ak. Right? So if I'm able to say, if I set, let's say this to be the solution itself, right? I just set x to be congruent to, let me just put y1 itself. Okay? So I know y1, a1, m1, right? So let me just put y1, a1, m1 mod n. So what happens? this definitely satisfies the first congruence, right? X1 is congruent to X is congruent to A1 mod N1. But what about the other congruences? That we don't know, right? So this term, when you divide by N2, I don't know what remainder it is. The only thing I know is when I divided by N1, it is remainder A1, which satisfies the first equation, first congruence. Now, what I can try to do, now I want my solution X to leave a remainder A2 when divided by N2, right? So I probably set X is equal to Y2 A2 M2, right? If I set X to be this integer, when I divide by N2, it will certainly leave remainder A2 because Y2 is the multiplicative inverse of M2 modulo N2. So these two things multiplied together will become 1. So X, when you divide by N2, it will leave remainder A2, right? But what will be the trouble? Right now, I cannot say anything about what will happen when I divide it by N1. So one possible guess is add both, right? Y1 A1 M1 plus Y2 A2 M2. Right? Define this to be X. Now, if I divide by N1, right, it will leave remainder A1 plus whatever remainder this will leave when divided by N2. But what will this leave? What will happen when I divide this by N2?
It will become 0.
It will become 0. Why is that? Because M2, I know, will have N1, N3, so on up to Nk divided by N2. Right? So when I divide by N2, it will have remainder 0. So M2 is essentially N2 times some number, right? So if I divide it, it will go to 0. So this term will go to 0. This term will remain. So is this clear, the idea what is going on? So I will write down the solution and then prove, right, for me. So I have to write Y1 A1 M1 plus Y2 A2 M2 plus so on plus YK AK MK. Maybe you can take some time to like digest what is that. So to show that this is indeed a solution, I have to prove that each such congruence that I wrote, right, the system of k congruences must hold true, which is what we have to do now. Right? But the idea should come naturally in the sense that first you try this one, right? But then the problem is you don't know what will happen when you divide this term by n2. But you know what will happen when you divide this term by n2. So add both. Surprisingly, the GCD of n2 and m2 is 1. Right? They are relatively prime. So this term will go to 0 when you divide by any other n. Right? So things will remain. All the congruences will be solved exactly. Right? So let's try to argue that formally, like whatever I said in English. So x minus y1 a1 m1 plus yk ak mk, right, is exactly equal to 0. And ni divides 0. So this is congruent to mod n. This is another way of writing it. Okay. So now what do I want to argue? If I look at yj, aj, mj and I go modulo ni, I should get 0. Okay. So let's just look at mj, right, where j is not equal to I. This I know is my n1 to nk, right, divided by nj. So it's this product that does not contain nj alone. So that is what I'm writing like this, n1 to nk divided by nj. Right, so this definitely contains ni, right, times some other integer p. So p is exactly this, right, where ni alone is here. So this means that mj mod ni is equal to 0, because mj is multiple of ni, right, for all j not equal to I. Right? So if I look at the congruence x, this term here, if I go modulo ni, everything will vanish except the term yi, ai, mi. Only that will survive. Everything else will go to 0. Is that clear? So x is congruent to yi, ai, mi mod ni. But what do we know about yi and mi? They are multiplicative inverses of each other modulo ni. Right? And such a thing exists because the GCD of ni and mi is 1. So I know that this is congruent to ai mod ni, right, for all I, 1 to k. So this is indeed a solution, right, to the system of congruences. So this is the answer. So whenever you are given a system of equations as congruences, first what you do is, let's assume that they are relatively prime. Right? You know n1 to nk. You compute m1 to nk, then compute the multiplicative inverse because you know that the GCD is 1. Right? You have the extended Euclid's algorithm to compute the multiplicative inverse. Now you know yi, you know mi, you know ai. You can just add these and be confident that this is a solution and the given system of congruences. So this is also an algorithm. Right? This is a procedure to output the solution. Is this clear? There are questions. Let's just take that. So this is essentially the existence part, that there exists a solution. There is one more part that I need to argue, which is the uniqueness. But at least the existence should be clear.
It's clear, ma'am.
Okay. So let's move on to the uniqueness, right? So any other solution will be the same modulo capital N. That's what I was. Let's suppose there is another solution. Let us call that solution y. So that's also an integer solution, right? So what I know is x is congruent to ai mod ni for all I in 1 to k, and y is also congruent to ai mod ni for all I in 1 to k. Okay. So now what can I say from this? I want to say that x is congruent to y mod capital N. Is that true? So this means that ni divides x minus ai and ni divides y minus ai. So what can you say from this?
X minus y is congruent to 0 mod ni.
Right. So ni, you know, is ni divides x minus y. Right? In other words, x minus y is congruent to 0 mod ni. So this means that the product of all these numbers also divides, right? This because this is true for all I. Right? This is because the GCD of these ni's is 1. Right? So it has to divide the product. I mean, the product has to rather divide x minus y. Right? So this means that just by definition, that x is congruent to y mod capital. So that there exists a solution, and if two of you come up with two different solutions, and if you divide them both these solutions by capital N, you will get the same remainders. To that extent, this is unique. So any solution to this system of congruences will be unique modulo capital. So now one question that you might ask is, what happens when these ni's are not relatively prime? So I will state the generalization of CRT, but we won't prove this here. So A, B, N are all integers, right? And I have two equations. X is congruent to A mod N, and X is congruent to B mod N. Right? So I want to say that there exists a solution. This is actually a slightly stronger statement. If and only if. So what can you say about these numbers? Okay? The A1, A2, AK, and these numbers A1. Yeah, we will not prove this. It is slightly complicated, at least in the interest of time, but I'm writing it in case you want to give it a try. Modulo the GCD. Okay, but this is only when there are two congruences. Okay? And this X is unique modulo the LCM. So this is a generalization of the Chinese limit theorem when we do not know any relatively co-primeness of it. Yeah, we will not do this. This is just for you to know that there exists a generalization. Okay, so if this is clear, then we'll move on to the next topic. Okay. So let's look at something else, so these are all, so whatever you've seen so far, all of these are tools that we will use in this lecture, in this description of the protocol called RSA. So it's culminating towards it. I mean, that is the point. Right? These are basics of number theory. And there is this very celebrated security protocol that is built just on the basics of number theory. Like you don't have to know anything fancy. So that is what we are trying to hit. But to do that, we need some more tools. And that toolkit is what we are developing now. So let me just define the next notion. Euler's quotient function. I'm not sure if you've heard of this. So we saw about counting primes, correct? So given a number, you can count how many prime numbers are there from 1 through that number. We saw this sieve method, or even counting, right? You can look at all numbers between 1 to square root and test whether it is composite or not, and so on. Now you're given an integer, and you want to check how many co-prime numbers are there from 1 to n to that number n. Okay. So let's say the Euler's quotient function of n, right? So it is the number of positive integers up to n that are co-prime to n. Okay? And this is denoted by phi of n. This is really important. It's super important notion for people. Okay, so is the definition clear? What it is? So, for example, if I ask you what phi of 10 is, it's phi of 11. Can someone count? Let me give a smaller number, so phi of 6.
2 for 6 and 10 for 11.
Sorry, I didn't get what numbers you said. You said two numbers?
Yeah, two numbers for 6 and 10 numbers for 11.
I didn't get how to write 4, 6. I mean 4 here and 6 here. Is that what you're saying?
No, I'm saying two numbers for 6 and
Oh, okay, okay.
Yeah.
So you mean this, right?
Yes, ma'am.
Okay. And this is 10. Okay. Okay. So here is a simple exercise. For a prime p, what can we say about phi of p?
it will be p minus 1.
P minus 1, right? All numbers are from 1 to p minus 1 are co-prime to p. Okay, so now let's try to do something. What can we say about for a prime p, p of p to the k? If the k is some like positive integer. So we have these numbers 1, 2, 3, so on up to p to the k. What was it? Can you just repeat it loudly?
P minus k. P to the power k minus k is like only those p power stuffs won't be there. Otherwise,
This
everything-
one, this
Yeah.
number.
Yes, I think so.
Okay, let's go at what we say. Okay, so now we want to count the number of numbers that are co-prime, right? To p to the k. So let's write this in blocks. 1, 2, 3, so on. 3.
But there also will be numbers 2p and like
Right, right. Yeah, that's what we want to see. Right? How many numbers are there? Did he miss anything or not? Up to p. Then there is p plus 1, p plus 2, so on up to 2p. 2p. Okay, I want to move that forward. Plus 1, 2p plus 2, so on up to 3p. Keep doing this and finally we'll get p to the k minus 1 times p. So how many numbers in this block, right, are co-prime to p?
1. P
One,
minus
right?
1.
So there is one number that is not co-prime to p, that is p. Is that correct?
Yes.
Okay. So there are like p to the k minus 1 many blocks. Right? And in every block, there is one number that is not co-prime to p to the k. Is that fine with everybody?
yes, ma'am.
Okay, so how many numbers are there? Number of co-prime numbers.
P to the k minus p to the k minus 1.
So it's p to the k minus p to the k minus 1. That is p of p to the k. So I can also write this as p to the k minus p to the k by p. 1 minus 1 by p. So now here is, so we saw that for any prime number, this is true, right? It's p minus 1. So now what can you say about any number? Any n. What can you say about phi of n? What's the most natural thing to do? What do we know about any number in relation to primes? Right? I'm given a number n, what can I say about its relation to primes?
It has a unique prime factorization.
Yes, it has a prime factorization, right? Uniquely, that's what we saw in the fundamental theorem of arithmetic. So n I know can be written as p1 to the k1, p2 to the k2, so on up to some pr to the kr. So this is the fundamental theorem. Now, phi of this is phi of this whole term. I'm going to write this as p1 to the k, phi of p2 to the k, pr to the kr. If this is true, right, then I know how to estimate phi of p1 to the k, right? So it's p1 to the k1, right, times 1 minus 1 by p1, p2 to the k2 times 1 minus 1 by p2, and so on. Right? pr to the kr times 1 minus 1 by pr. So it's essentially what? p1 to the k1 times pr to the kr times product over p prime 1 minus 1 by p. So this is the number n itself. Is this over all primes, this product? Or what kinds of primes?
Prime factors of n.
Prime factors of n, right? So in other words, p should divide n. Is this clear to everybody? So this thing here, okay, this is called the product formula. So this is quite famous. Product formula for Euler's torsion function. But I used something here which we did not do. What is that?
Multiplicativity.
This one, right? That you can actually write phi of p1 to the k1, p2 to the k2, so on up to pr to the kr as phi of p1 to the k1 into phi of p2 to the k2. So what we did was just sort of took this p and applied it independently to the multiplicators. So this is something we did not prove, which we should. So what is it? Right? So this property is called multiplicativity of phi. Right? In other words, for phi of n can be written as P of m times P of
GCD m comma n should be 1 for this.
So what will happen if the GCD is not 1? When do you have an example where it will not be multiplicative? So he's saying that this holds when m is co-prime to n. Right?
5 2 into 3, 5 6.
Sorry, so what is m and what is n? It is not clear.
Oh, that is not an example. Yeah, sorry.
So the claim you are saying is that m is co-prime to n, right? So can you give an example? Like how did you figure out that m and n should be co-prime? So
Oh, I
some
probably,
example.
I probably saw this earlier and I forgot.
Okay. Okay. So yeah, we will see why they should be co-prime or they should be not co-prime and so on. So this might seem like a really stupid thing to sit and prove, but I'm going to prove this because this involves something that you just saw. Okay? And it's one really nice place to see things being applied, right? Whatever you have just seen. So let's try to prove this. I will keep m co-prime to n for now, and then let's see whether it should be removed or not. So now, for now, don't think about the conditions on m and n. So you have two sets. One is the set of numbers that are co-prime to mn. The other side is the set of numbers that are co-prime to m and co-prime to n, right? The product. So now I want to say that these two sets are the same, in the sense that the number of numbers or the cardinality of these two sets are the same. That's what I want to show. So how do we do this? That's the first thing to ask, right? So we saw this in set theory. We're giving two sets and we want to show that they have the same cardinality. What should you do? What should you exhibit? So this is the number of numbers that are co-prime to mn, right? So let's take the set S1 to be all these numbers that are co-prime to mn. So what is this? You can think about this as all those numbers in 1 to mn such that the GCD of a and mn is 1. So this is essentially the definition, right? So what can you say about the cardinality of S1 by definition?
Phi of m.
Phi of mn. That is just from the definition. Now I want to argue that the size of this set is phi of m times phi of n. So I must define another set, right, that has so many elements, these many elements. Right? What is a natural candidate for that? That has phi of m into phi of n elements. Yeah, given you a hint there. So look at all elements that are co-prime to n. Look at all elements that are co-prime to n. What should I do to these two sets, the operation to get these many elements?
Consider pairs of such elements.
Yeah, consider like Cartesian product, right? Something like the product, Cartesian product. So you have BC, where B is numbers from 1 to m, right? Such that the GCD of B and n is 1. And C are numbers from 1 to n. GCD Cn is equal to 1. Right? So these two sets. What is the cardinality of the set S2 from definition?
Phi of m, Phi of n.
Phi of m times phi of n. Right? So now I have two sets. One set is S1. The other set is this set S2. And I want to show that these two sets have the same cardinality. So what should I exhibit? A bijection, right? So this is something you have seen in combinatorics, how to show that two sets have the same cardinality. So I want to exhibit a map psi that takes elements in S1 to S2. And I want to say that this map psi. So first I have to define the map and then I have to define a bijection. So what is a reasonable map that takes in A mod Mn? Okay. So this contains numbers from 1 to Mn. Right? So if you go modulo Mn, it's fine. Any A is going to be itself, right? And element here, element from 1 to Mn. I want it to go to two elements, 1 to M and 1 to N. What should I do?
First divide by m, then divided mod m, mod n.
Right? This is like the most natural map. You have a number which is in the range 1 to m, and you want to split it to two numbers in the range like 1 to m and 1 to n. And what you can do is divide and take the remainder. Then you will definitely get like two numbers. So this is certainly a map from S1 to S2. Now I want to argue that this is a bijection. Okay. So the claim is that psi is a bijection. So for this, I have to argue two parts, right? First, it's 1 to 1, and then it's 1 to 1. Suppose I have two things A1, A2, both are in the set S1. Right? A1 is not equal to A2, and both their images are the same. What can you say? So they go to the same they go to the same element in S2.
M divides A1 minus.
Okay. So what will happen? That's the case. Then A1 minus A2 can be written as some k times Mn. And because M and N are relatively prime, you can say that A1 should be equal to A2. Right? Another way of seeing this is you look at a number, right? Some number here or some number here. Then divided by M, it leaves a remainder A1. I mean, this is the number here, right? So A1, when divided by M, leaves some remainder. And A2, when divided by N, leaves a remainder. Right? Both of these reminders are the same. So A1 is congruent to B mod. Okay. Is this clear? So can we say that A1 is congruent is this true? Can someone see why this should or not be true? Leave this as exercise. So this is via Chinese remembering. Okay. So what the Chinese remembering theorem tells us can actually be stated in a slightly different way. That if so you nice way to see this is in any congruence, right? You can like these two, right? So x when you divide by n1 leaves a1, or the other way around is also true. So a is congruent to b mod n is the same as saying that b is congruent to a mod. So now it is tells us that if a1 is congruent to x mod n1 and a2 is congruent to x mod n1, then there is such an x, right? So there is a number that is that satisfies all the solutions and is unique modulo the capital N, right? Which means that to divide by, you can flip these two and see that this solution also satisfies the same numbers modulo the products. So this I believe is an exception, but it's a very nice congruence of Chinese corollary of Chinese remainder theorem. That if A is congruent to B mod n and A1 is congruent to A2, right? So A2 is congruent. I hope I didn't mess up. Yeah, B mod n. Then can I find the solution modulo Mn? Find the solution. Right, from the solution to these modulo Mn. So what can you say about B mod Mn? But another way to see what he said was that we know that the GCD of A1 with Mn is 1, A2 with Mn is 1. So Mn divides A2 minus A1. Okay, so when M and N are co-prime, this would imply that A1 should be equal to A2. Because all prime factors of Mn divide A1 and also divide A2. and they are co-prime. So A1 should be equal to A. So this is why you need this requirement of co-primality to show that it is on to. What do we mean by it is on to? I know that for every solution on the, like every point on the right hand side, there should be one on the left hand side, right? So if I take a BC, right, in S2, I must say that there exists an A in S1, right, such that A is congruent to B mod N and A is congruent to C mod N. Why is this true? Why should there exist a solution like this?
Chinese remainder theorem.
Right? So by Chinese remainder theorem, we know that there exists a solution A that satisfies the above congruences. Yeah, this question I didn't actually frame correctly, so I will give this in the assignment. Okay, so what can you say about congruences mod MN? That's what I want to say, but I think I didn't frame it correctly. Yeah, I will frame the question for the assignment. Okay, so this also shows multiplicativity, but more than that, it shows that you can actually use Chinese remainder theorem to show that certain functions are surjective. Functions of this kind. So I have 10 minutes, but I may overshoot like 10 minutes extra. So I want to, now we have seen what quotient functions are, we understand what it is. So now we want to actually prove the real hero behind all this, which is Euler's theorem. So in Fermat's theorem, if you remember, what did we show? For any prime p, we showed that a to the p minus 1 is congruent to 1 mod. And at that point, we had asked this question: what if p is not prime? What are the conditions under which we can say that there exist solutions? Something like a to the k is congruent to 1 mod. Or can we say something like that? Something similar to Fermat's theorem, but in the case of composite numbers. So here is the actual generalization of Fermat's theorem. So let a and n be integers that are relatively prime. Then a to the phi of n is congruent to 1 mod n. Okay. So actually, I think Fermat's theorem came up earlier, or not, I'm not sure. But now if you just set n equal to prime, right? Suppose n is any prime number, then what do you get? A to the phi of n. And what is a to the phi of n? Let's say p is a prime number. What can you say about phi of p?
It's p minus 1.
Minus 1 is congruent to 1 mod. So Fermat's theorem is actually a special case of Euler's theorem. But we saw that first because that's much easier. And we didn't have the machinery then, right, to state Euler's theorem. Okay. So now, yeah, this is a really interesting statement. And yeah, this can be used to solve like really strong congruences. And evaluate strong congruences. So for Fermat's theorem, you remember this, right? We could do modular exponentiation better, like some 7 to the 222 mod something, and I was able to evaluate. Similarly, even this can be used to evaluate some 7 to the 22 mod 11 or something like that. Right? Such equations, you can express this, where this number is related to phi of 11. Right? You can use that and substitute everything to 1, because you know that modulo n, this is congruent to 1. Okay? And this certainly has applications to cryptography. That's why I want to prove this. So here is a proof. It's not very non-trivial, but let's do this. So what is the set we are interested in? I have a number n, and as usual, we are going to look at all numbers that are co-prime to n. So consider this set k co-prime to n. Okay. So how many elements are there in X?
P of
P of n.
n.
Okay. P of n many elements are there. Let's name these elements. X1, X2. This is the set. Now, Can xi be congruent to xj mod n in this set? Is this possible?
No.
Suppose it were, right? What will happen when n will divide xi minus xj, and all prime factors of n must then divide prime factors of xi minus xj, and prime factors of n must be the same. Okay? Whatever. So this will be something like kn is equal to xi minus xj. Then all prime factors of this number should also be prime factors of this number. Right? But we know that these are all numbers that are co-prime to n, so they cannot share any prime factors. So this is not possible. So they're all incongruent, not n. Right? In other words, these xi's are co-prime to n. GCD of xi comma n is 1, then none of these can be congruent modulo n. So another way to say this is these are incongruent model. So some textbooks use that term. So you must be familiar with that. Now we are going to do something that we just did for Fermat's theorem. Right? So in Fermat's theorem, we considered two sets. One set had the set of elements that we are interested in, right? 1, 2, 3, so on up to 3. What was the other set? It was like A, 2, A, 3, A, so on. Right? So similarly, we are going to consider another set. AX1, AX2, so on to AX3. So now what can you say about AXI and AXJ? Are these congruent model? Suppose this is true, right? AXI is congruent to XJ model. Can we say that XI is congruent to XJ model? Can I cancel this? For any A, is this true or what?
The GCD of A and N should be 1.
Yeah, so for all A's that are co-prime to N, I can do this. So consider an A which has, so A here, right, is co-prime to N. So the A is given to us and it is co-prime to N. So we know it is co-prime to N. So here this condition is true. Right? So what I'm trying to say is, let's look at this set P by going modulo N. Right? So you look at AX1 mod N, AX2 mod N, AX P of N mod N. Right? So if any two, the first question is, can any two elements in this set be equal, and what are the elements of this set? So we have one set here, which is the set of numbers that are co-prime to N. And here is another set which involves A. Right? So it must sort of occur to you that if I take the product out of all these elements, I will somehow get A to the phi of N outside, times there will be some additional products, right? Xi mod N and so on. So I have to work with that. So this A to the phi of N has come out. So this thing, I need something that is congruent to one model. Roughly that should be your plan. Right? That's what we are working towards. So here you have a set of phi of N elements. Here there are a set of phi of N elements. Now I want to ask, what can you say about these two sets? Right? So first let's look at elements in this set. Because you have gone modulo N, we know that all these elements are going to be less than N minus 1, right? They are between 0 and N minus 1. Now the question is, can they ever be 0? So can it be that Xi is mod N is congruent to 0?
No.
Can this happen? If this did happen, what can you say AXI is congruent to 0 mod N? Right? Then this means that N divides Xi. But you know that these Xi's are co-prime to N. Right? This is something new. So this cannot happen. So 0 is never allowed. It contains other numbers from 1 to N minus 1. Is that clear? Okay. So now, this is one observation. So let's look at another observation. What can you say about an element in T and elements in X? Right? So if you look at an element AXJ mod N, right, what can you say? between elements here and elements here. There are few of n elements in both these sets. The question is, are these sets the same? That's what I'm asking. Remember
Yes,
that
yes.
this set does not contain 0. So this set also first I should show does not contain 0. That is sanity check. Okay, 0 is not there. Now the question is, does every element here have an element here that they are the same, like a map? Somebody said the answer actually. I missed.
Yes, ma'am.
Okay, so why should it be true?
Because the elements in the in T should also be incongruent, modulo.
Should also be congruent, right?
Yeah,
Or did you?
I mean,
Yeah,
pairwise incongruent.
correct. So here is an observation. Every element of T is congruent. So yeah, so one claim is X is equal to T. This I will leave the proof as an exercise. I mean, it's not even an exercise, just for you to observe. 0 is not there. There are numbers from 0 to n minus 1. So one thing you must see is this has numbers from 1 to n minus 1 to n minus 1, right? So first thing you have to check is 0 is not there and all numbers are between 1 to n minus 1. That is definitely true about this. Now you can further also see that every number here has a number here. That they are the same. Maybe the ordering is different, the way in which it's written, but they're essentially the same sets. Right? So then what can we say? I know that AXI, right, is congruent to AXI mod n. Right? This is like trivially true. All right. So this means that every element here is congruent to one element here. Right? So AX1 mod n is congruent. So AX1 is congruent to AX1 mod n. AX2 is congruent to AX2 mod n, and so on. So I can take the product, right? And it is fine. So one side I will have product I equal to 1 to n xi, or maybe let's not go there. Xi is congruent to Axj mod n. So you cannot say exactly xi xi. So that thing I cannot say because it depends on the way I have written it, right? I could have written it in a different way. Everything I can say is that for every xi, there is an Axj mod n that it is congruent. Okay, so for all ij, 1 to c of n. That's why I did not write xi is congruent to axi z, because the ordering could be different. I don't know. Right? So the product of both the sets also I can take, because we can multiply across the congruence. So all this is from 1 to phi of n. Okay. So 1 times this is equal to this. Now I can take a to the phi of n outside. Xj mod n, 1 to phi of n. Here again, xi I equal to 1. Or maybe let's make it extra. Okay. Okay. So what do we do next? So this is 1 into this. So what should I do? To prove Euler's theorem, I have to cancel these two terms. To cancel these two terms, what should I prove? That this product is coprime to n, right? Then I can cancel them. Is that clear? So to cancel, we need coprimeness, right? So you can think about this as 1 times b is equal to congruent to a to the phi of n times b mod n. To prove Euler's theorem, I should cancel both b, for which I will need the b is congruent, b is coprime to n, right? And b here is the product. This is the b. Okay? So I'm going to leave that as an exercise. That if so, the individual terms are coprime to n. Right? So if a is coprime to n and b is coprime to n, then ab is coprime to n. Also, I must have one. This should be more in here. Just refresh. I don't know why I gave us this. So this product j equal to 1 to 3 of n, it's j is 2 prime. So I can cancel. I will get 1 is congruent to a to the c of n mod n. And I can also flip, right, whenever a is 2 prime. Yes, I did rush a bit in the interest of time. So please do try these exercises. Okay. So this one also. It's not at all hard to see, but just that I rush through it in the interest of time. Okay. So now there are many questions that you can ask, right? Given an integer, given a number n, how to compute the set, how to compute phi of n, right? Is it easy to compute? Is it hard to compute? Like if I give you some 100-digit number, can you compute it? For a prime, it's easy, right? You have to just, if I input p, I have to just spit out p minus 1. But what can I say about composite number n? Right, I have to do something like this. So I have to find all primes that divide n. Correct? And then n is really, really large. Right? Finding primes itself going to be really hard. For example, if n is some 200-digit number, then even if you, how do you compute or how do you find all the primes? Even if you use sieve of Eratosthenes or whatever method, you have to somehow run like say up to root n, which is also very, very large because n itself is like some 200 digits. So these are all things that we are going to use in cryptography. Right? So we want some, so when you send a secret, right, if Alice sends a message to Bob, what is the interest here? Only Bob should be able to read the message. Everybody else outside, for example, if there is a Charlie who is an enemy of Alice and Bob, he should not be able to read the message. So we should somehow encrypt the message in such a way that there is some difficulty embedded in it for Charlie, but everything seems easy for Bob. Okay? So this difficulty and other things will mathematically be rephrased in terms of Euler's functions and so on. Right? Whatever I said in English. Okay, so the whole of next lecture will be about cryptography, but we will use one like very important observation. It's a very simple observation though, but I'm going to just write it down. So if you find time, please work this out because this is like really important. So if x is congruent, so we saw many things, right? We saw modular exponentiation. We saw that computing this modular exponentiation is really difficult. When I mean difficult, you could do this in log case steps, like where it's the exponent, right? Logarithmic in the size of the exponent. But if exponent is very, very large, even this logarithmic is large. So now what in cryptography we want to understand, we would, I mean, when you see the protocol, you will be clear. But we want to ask whether a to the x is congruent to a to the y mod n. Okay. And this, like, how do you ensure? I'm given a to the x and I'm given a to the y, and I want to check whether a to the x is congruent to a to the y mod n. Is there an easier way to do this? Let's say x and y are small, but a is like super large. X is 1-digit number. So this is like say 3, this is 5. N is also small, right? But a is very, very large. It's some 100-digit number. So it's 1, 2, 3, 4, 5 to the 6. Is it congruent to 1, 2, 3, 4, 5 to the 7 mod n? That's the question. Right? So 1, 2, 3, 4, 5 is very hard. Right? I don't even know how to compute it, let's say. Right? It's some very large number. It's not even 1, 2, 3, 4, 5, let's say some 200-digit number. But these numbers are like small.
So
right? So is there,
the computation of phi n is at least as hard as factorization of a number. Is that so? Or is there
it
other way to
seems so,
compute?
right? It seems so because the one way to compute phi of n that we saw is the product
Yes.
formula. But for that, we need to know the prime factorization of the number.
Yes.
And which the other day I hinted out that it is hard. But we don't know if there are other ways, right? We have to see all that. But one thing you definitely know is if the number is prime, it's very easy. If there is no computation, right? So this is essentially what we will use in cryptography. So Bob, so whoever is the right person to know the answer, he will somehow figure out that it's a prime number and he can do it. Right? The other person, Charlie, who is the enemy of both Alice and Bob, will essentially have to compute phi of n, for which he has to factorize it. And factoring, we believe, is hard. So I will actually show you how much time it takes to factor this. I mean, show meaning there are some experimental analysis to say that it will take some 500 years to compute the factorization of this number and so on. So I will just show a table. I mean, that's just for information. But now the right person, right, he should be able to compute this. So these things might all be over the head at the moment, but after the next lecture, it will be clear. But what I wanted to say is, let me just fill off this. A is super large, so I don't want to compute a to the x and a to the y. That is not doing, because that will take 500 years, let's say. So I have to just work with x, y, and n. Okay. So here is the really cool thing, that if x and y are congruent modulo phi of n, then you can actually use them as exponents modulo n, also the congruence will be. So this is a really cool statement, and it's like very simple. Just apply Euler's theorem. That's all. And nothing fancy. So please try this proof. RSA will, the security of RSA, the protocol that we'll see next time, will depend on this statement. Okay. But I will formally define what cryptography is, what a crypto system is, who is Alice, who is Bob, what are our goals, right? When you send a secret message. Okay, so these things we will see in the next lecture. We will not begin with RSA, we'll begin with some sort of ciphers, like how message passing was done in the time of Julius Caesar. Okay, so this cipher is called Caesar's cipher. It was the first ever encryption that was used, right? So Caesar wanted to send a message, and what he does, right? How is the king on the other side who is authenticated to read the message will find the message, but none of us will be able to figure out, right? Is this true? These kinds of security notions we have to define. It will take some time, but please be like familiar with Euler's theorem and congruence, because we will just believe that I will just believe that you know everything until now, like whatever we have covered. Okay, so I will just stop recording, and then if there are questions.
Recording stopped.
Okay, so yeah, we will release one assignment maybe end of this week, but deadline will be after the end semester. Okay, so if there are no questions, let's meet on Thursday. I think this link should work on Thursday also. The same link. Otherwise, anyway, I will put out a message. So please check the Moodle once before logging. Okay, then see you all on Thursday.
Thank you, ma'am.